Hello, those who are watching this online. This is Semester 1 2023, and this is a revision seminar for Intro to Math Econ 1. And we're going to be talking about some multivariable derivative things. All right. Is that working for you? Cool. Okay, well, I've got an example here, a question that we want to try out, and I'm just going to read it out. It's from the notes. So given the utility function u, which is equal to x1 to the power of a half times x2 to the power of a half, find a general expression for MRCS in terms of x1 and x2. Okay, calculate the particular value of MRCS for the indifference curve that passes through 300, 500, hence estimate the increase in x2 required to maintain the current level of utility when x1 decreases by 3 units. Oh, okay, cool, there's a lot going on there. The first thing we want to know is what MRCS stands for, and we already looked at the previous page, those of us who are here, and said that MRCS is the marginal rate of commodity substitution, the amount by which one input needs to increase to maintain constant value of utility when the other input decreases by 1 unit. Okay. All right, so there's these two goods, x1 and x1 and x2 is how many of each of them there is. And then when the utility stays the same, that's called an indifference curve. Cool, I'm just going to start talking about that properly. I'm just going to get a pencil, which I seem to have lost. That's what I'll do. Okay. I shall give the title Multivariable Things and we'll see where we go. So when you have a utility, now this is not technically a maths thing, the word utility, that's an economics terminology. And the idea of a utility is that we are imagining how human brains make decisions, which is what a lot of economics maths is about. Either collections of individuals and how they do things collectively, or a single individual, and this is a single individual thing, and we're saying that there are two goods that they may or may not want to buy, and a combination of the amounts of the two of them, x1 and x2, this is saying how useful we think it is. And so this is the idea is that u is, it's not really, but this is my imagining of it. How useful to us x1 and x2, that combination is. And so you're going to be more likely to buy things that are more useful to you. That's the idea. And so you want the combination x1 more if u is higher. That's the idea behind it. And so an indifference curve is made of combinations of x1 and x2, all with the same utility. The same value of whatever u works out to be. And the reason it's called indifference is the word indifferent means that you don't care. And so you're saying that, well, this one, I don't care about having this option or this option because they've got the same usefulness to me. That's the idea behind it. And so indifference curves have the tendency to produce shapes like this. Okay, cool. So that I'm good with, and I'm not even going to answer the question yet. I am just going to say that I can find indifference curves for this, and the idea is that what you do is you draw pictures of the x1s and the x2s, and this is how many of the whatever commodity 1 is that we buy, and this is how many of commodity 2 that we buy, And the u isn't drawn on this picture at all. Every point here has a value of u, and they all have a number of their own. And what I want to do is you could imagine coloring them all in with red if they're bad, and green if they're worse, and green if they're better. And so what you'd want is a line where they're all the same color, and they'd be indifferent to those ones. And so I can draw curves on here, but I need to figure them out first. That, every point has a value of u. So they all have different values of u at different points. There'll be a number here, and maybe it's 30 here, and maybe here it's 50, and maybe here it's 20, and maybe here it's 10, and maybe here it's 100. Every point has a number of its own. So in my head, it's like an advent calendar, counting down to Christmas thing with a door, and you open the door and there's a chocolate behind it. And so each one of them has a different amount of chocolate, and the ones with more chocolate are better. So that's my idea of how I think about it. So if I want an indifference curve, I'm going to need to pick a specific value of u and to figure out a formula for how x2 is related to x1, because that's how you draw graphs on a graph like that. So to draw indifference curves, if you're very lucky, you'll have a computer that can do it for you. So I can actually do that. Just give me one moment. Oh, there's all my socials. This is the Desmos graphing calculator, and it doesn't think in x's, x1s and x2s, it thinks in x's and y's. So I could say, for example, that u of, so I could pick an answer for, I could say that u is x to the power of a half, y to the power of a half, like that. Oh, poo, it's not going to, there's something weird going on there. And I could tell it what the answer is for u. So u is 20. Of course not. I might have to do it this way, equals u. But there it is there. That's when u is 20, and, damn it. That's when u is 1, and that's when u is 3, 4, 5, 6, 7, and you can change the value of u and get all different answers. And so this is where u is equal to 20, this is where u is equal to 12, this is where u is equal to 5.8. And Desmos is pretty good at doing that sort of thing for even the craziest of functions. And it can give you a feel for what's going on. Not that you can use that during your exam, of course, but it does help you to draw it as you go, and it might be really useful if you do more math things or even economics things to get a handle on what it should look like. But if you want to draw them by hand, you're going to have to say, pick a value of u, and so that everybody knows that you've picked a specific value of u and you're not thinking about all the values of u that could be, you normally call it u0 that they talk about. I don't know why 0. The 0 is the one that I'm thinking of at the moment. And so then you can say, all right, so x1 to the half, x2 to the half works out to be this specific answer. And so then you would continue working until you got to the point where you could get x2 equals in terms of x1. That's the goal. So the goal is x2 equals something involving x1. That's not an xi, sorry, x1. That's the goal, some sort of formula on this side involving x1. And so the first thing that bothers me is the fact that this x2 is attached to all of this, so I'll divide by that. Is that okay, dividing by the x1 to the power of a half? And because the half is powers are stickier than times, that'll carry with it. And then to get rid of a half power, I will have to do a squared. And so therefore the x2 will be all of this squared, like that. But I could also powers interact with division by doing each bit separately. I can do that. So that's the same as u0 squared divided by x1, like that. So I can keep the x2s there so it's easy for me to process. Now it looks like this. I have to use my knowledge of what graphs ought to look like to be able to make sense of that. And so if this was a 1 over x1 would be like this. Because in my head, y equals 1 over x looks like that. That's what y equals 1 over x looks like. And then multiplying it by a number will mean that the whole thing will be higher. And so this might be for you when you get 1 over x1 squared, 1 over x1. But then if it was further, everything was higher up, damn it, that's such a bad picture. It might be like that, all a bit higher up. And this maybe would be 4 over x1, and you could choose different numbers and they would get further and further out. That's the idea behind it. So this is a really common utility curve to get, because in your Cobb-Douglas version, it's always x1 to some power and x2 to some power. And so you'll often get something that looks like this. And it will look like this even if it's x1 to like x1 squared or something on the bottom. They'll all look similar to this. But x1 squared will be sort of closer in at this end than that end. But they'll all look like this, and utility curves have the tendency to look this way. And so even if you didn't know what it should look like, probably just drawing some random curves that bend inwards like this is probably right. Okay, but if you're not sure of exactly what it should look like, this is what it should look like. Does that answer that question about how to draw them? Okay. So that's drawing the indifference curves, and one of these is the right curve that we're going for this question. So the second thing I want to say is I want to understand this marginal rate of commodity substitution. And what your lecturer said was that this was how much x2 has to go up by to maintain constant utility when x1 goes down by 1. So this is x2 go up to keep constant utility when x1 goes down by 1 on average. So the really important thing I've noticed in this sentence is that it says to keep constant utility, and having constant utility is the same as being on an indifference curve. So that means you have to be on an indifference curve to do that. So this is really interesting to me. If you're on an indifference curve, I'll just draw a new picture. New picture. So here we are on an indifference curve, and here we are at the position x1, and that's x2, like that. Those 2 points together make the point x1, x2. And they're saying that if the x1 goes down by 1, which means we're going this way, how much does the x2 have to go up by? So we're going to track along the curve this way. And we're going to say, going to go down by 1 this way, and this is the marginal rate of consumer substitution, how much the x2 has to go up by to compensate. Of course, it's a curved line, so technically it's not that. It's only what it is when you're really close to this point. So it's an on average, if it went down by 1, how much it would go up by. But it's more like if it went down by 0.01, how much would that go up by in 0.01s? Like, so as opposed to, yeah, so it has to be really small changes, but that's the idea behind it. Okay, and so this is, that thing is minus the slope of this line. Yeah? So that's great, slope of this line is this. So the marginal rate of consumer substitution is minus the slope of the indifference curve. And that's interesting because it's going to have a slightly different slope at different places. And so what the marginal rate of commodity substitution is it's going to be a formula involving x1 and or x2. Okay? So if I could find a formula for what the indifference curve was, I could differentiate it, and that would tell me the marginal rate of consumer commodity substitution. But I don't have to do that. There's an alternative way of doing it. And so if I've already gone to all the effort of finding this, then I can differentiate that and that'll give me the answer. So there's 2 ways to attack it. So there's this, it's minus the slope of the indifference curve, but there's also another formula, is that it's du on dx2, sorry, du on dx1 divided by du on dx2, I think, yeah. So there's 2 alternative ways of doing it. So either we have to find the formula for the indifference curve and differentiate it, or we can do this calculation instead and they will give us the same answer. But one answer will be purely in terms of x1, and the other answer will be in terms of x1 and x2 at the same time. So that's the difference between them. So for this question, you were explicitly you weren't told to find the indifference curves, and so we're not going to do that. So we're going to start again, but I just did want to talk about what the indifference curves were doing. So du on dx1, and this is a curly d because there's 2 variables here, and so we're picking one of those variables. I call it partial d du and partial d1. So dx1, in this case, dx1 is the variable, and x1 is the variable, and x2 counts as a constant. So constants multiplied on will still be multiplied on afterwards, and then I'll have to multiply by the current exponent and make it go down by 1. Great. And then du on dx2, this time the x1 counts as a constant, and so that x1 to the half will still be there, and then I'll have to multiply by the derivative of this bit, like that. And so the marginal rate of commodity substitution is du on dx1 divided by du on dx2. And this is a half of x1 to the minus a half, x2 to the plus a half. That's what this formula worked out to be. And this formula worked out, I'll put the half out the front, x1 to the plus a half, x2 to the minus a half. I just move that half to the front. So I can cancel the halves. Good move, awesome, great noticing. And then, okay, sure. Now I know that I can treat this as 2 separate fractions like this. And when you divide 2 things that have the same base, I subtract the powers. And so I'm going to get x1 to the minus a half minus another half, which is minus 1. And this one will be x2, and it'll be a half minus a half, which is plus 1. And so that's the same as x2 divided by x1. You okay?
Yeah.
Cool. There's lots of ways I could have done that, but this is probably the quickest one. And so here I am, that is the marginal rate of substitution, the marginal rate of commodity substitution in terms of x1 and x2. So if I know exactly what x1 and x2 are at the moment, then I can figure out the marginal rate of commodity substitution if I know what both of them are. So I know that, so at the point 300, 500, the marginal rate of commodity substitution is x2 divided by x1 according to this calculation here, which is 5/3. So that's telling me that for every one x1 that I lose, I'm going to have to gain 5/3 of an x2 in order to maintain the same utility. Now that will technically be different at different places on the utility curve. At this point, it's this. Yeah. So the way that this sentence is written is it seems to say that for the entire indifference curve that passes through this, the MRCS will be the same. I'm not sure I believe that, but I could be wrong. I could be wrong. And so that means that for every one decrease in x1, so for x1 going down by 1, we need x2 to go up by 5/3 to keep the utility the same. That's what it says. On average, but only if it's small, right? So if it went down by 0.1, you'd have to go up by 0.1 times 5/3. And if it went down by 0.3, you'd have to go up by 0.5 by 5/3 times 0.3. And so this is saying that if you want to estimate the increase in x2 required to maintain the current level of utility when x1 decreases by 3, well, if x1 goes down by 3, we need x2 to go up by 5/3 times 3. Yep. Which is 5. Now this is my working, but that's sort of what I'm doing. You're allowed to write it more like this. This is how I think about it, and it makes sense to me, but it might not make sense to a person reading your exam. What they would normally say is that the change in the way the marginal rate of substitution works. So the marginal rate of commodity substitution was 5/3, and so that's saying that if you change x1 by a certain amount, not xi, you change x1 by a certain amount, you have to times by 5/3 to get the matching change in x2. Yeah, though technically it's minus, but it's like the downwards x1 change matches with an upwards x2 change. And so you've got minus going down by 3 times 5/3 is what the change in x2 is going to be. Yeah. Crap. There we go. Should have written it around this way. So that's what the marginal rate of substitution says, that if you change the x1 by this much, the x2 changes by 5/3 times as much. And so minus 3 is plus 3, and plus 3 times 5 is 5. Right, that's the calculation that's on the notes here. How do you feel about that?
Yeah, that actually makes a lot of sense.
Yep. And it is theoretically possible for us to figure out what the utility is at this point, just to point this out. So it wasn't in the question, but at this point, the utility is 300 to the half times 500 to the half, which is whatever it is. We don't technically need to know what the utility is, but I just thought I'd point it out. 300 to the power, to the power of a half times 500 to the power of a half is 387.3. Well, maybe 2. No, 30, rounded off to the nearest 2 decimal places. That would make... Yeah. But I just did it straight with the powers exactly as they were written. Yeah. So that's what it is. And so this entire indifference curve all have that same value of u. Yeah. But I could just as easily, if I had already gone to all the effort of finding the utility curve, I could have differentiated this instead. And there'd still be a u naught squared there somewhere, but I would have to figure out what the u is and sub it in. Yeah. So it should all have worked okay, fingers crossed. Okay, there you go. So that's that question. And the marginal rate of technical substitution is the same sort of thing, but instead of having x1 and x2, you have L and K, but it's all the same. Yeah. Yeah. And instead of calling it a utility, an indifference curve, they call it an isoquant. It's the same idea. Iso means same and quant means amount. So it's the same amount. So I guess a utility, an indifference curve is an iso utility, I suppose. But that's what that's saying. But it's the same idea, but it's just, this one is about the utility is about an individual person's behavior, what their thoughts are, whereas this is about an entire society's usage of labor and capital. Yeah, but it's, pardon me, it's the same idea. Right, I'm feeling good. I might just write that down. So it's possible to have, so for a whole, so for production, which could be for a society or a factory or whatever it is, you have a quantity is some function of K and L. So in this example, it was Cobb Douglas. Oh crap! I'm just going to do it. Something like that, where this is a number. It's just some sort of random coefficient, and this is capital, and this is labor, and this is the quantity of things that are produced. And this is some sort of number we multiply by to get the right answer. And then these are, I don't know if these things have names, but they're just powers, like exponents. And then you can wonder, well, if I lose capital, how much labor would I need to keep the same amount of production? It's a similar sort of question. So if we lose capital, how much is it? Labor? If we lose labor, how much capital do we need to? Yeah. If lose labor, how much capital? How much does capital have to increase to keep the quantity the same? And that's the marginal rate of technical substitution. But it's exactly the same idea. And you do the same formula, but with K's and L's instead of X1s and X2s. Yep. Sweet. So I will just make the comment, same idea as utility marginal rate of commodity substitution. So marginal rate of technical substitution will be dq on dl, dq on dk. Yeah. And it'll be the same sort of picture. That's L and that's K. It'll be similar, pretty much the same. And that's why they're together in the course, different concepts, but the same maths. Right, that's that one. And so there's all these different practice problems which are similar concepts. Yeah, all right, I will leave you with those. Okay. Feeling better about that? I'll have to scan these afterwards and I'll put them on the website. Just chill, I can scan them and then bring them back and you can have them if you want. That's the luck of being the only person there. Oh, yeah. We'll get there. So, which one?
The second question.
Number 2 here? Oh, 3 variables. Oh, look at them being annoying. I'll just need to get some more paper. You're being very gracious. So f of x1 and x2 and x3 is x1 times x3 cubed over x2 plus ln of x2 times x3. Let's just make it complicated. Find the expression for all the first and second order partial derivatives and verify that f12 is f21 and f13 is f31 and f23 is f... Okay, sure. Okay. So let's do all the derivatives. That's what we're going to do. All first and second derivatives. So when they say f1, they mean df on dx1. And so what that means is I treat everything that isn't x1 as a constant. And so this x3 squared is multiplied on, and so it'll still be there afterwards. x3 cubed. This x2 is divided, which is the same as multiplying. That'll still be there afterwards. And they're constants, so they'll still be there. And the derivative of x1 would just be 1. And then this doesn't involve any x1s, and so it will disappear entirely. Is that all right? Let's do f2. So that'll be df on dx2. So this time, oh, that's not as pretty, is it? The x2 is on the bottom of my fraction. So it might be easier to just rewrite the original function momentarily. I have imagined that as x2 to the power of -1. So the x1, x3 cubed counts as a constant and it's multiplied on. And my x2 is really an x2 to the -1. And so that would be -1 x2 to the power of -2. So that's that bit there becomes this. And then ln, when you differentiate something involving ln, you get 1 over whatever's inside it. Yep. And then you, because of the chain rule, I have to multiply by the derivative of whatever actually is on the inside. And the derivative of that, the x3 counts as a constant, it's multiplied on, so it's still there. And the derivative of x2 is 1. So when you differentiate an ln, you put 1 over whatever's in there, and then you have to multiply by whatever the derivative of the inside is, because of the chain rule. And so this is the derivative of that. We differentiate that and we get this answer. I can. So just as an aside, I'll come back to this. So the chain rule goes like this. If you have a function inside another function, this is how they write it down, and I'm going to make a bad thing of this, but if a function is one function with a different function inside it, then when you do the derivative, is this how you lecture it? Do they do the dash? When you do the derivative, you have to do the derivative of f as if this was just an x, and keep this thing inside it, and then times by the derivative of the thing that's inside there. So as an example, something stupid like that. If that was just an x, my derivative would be 7x to the power of 6. But it's not an x, it's an x cubed plus 5x. And so I have to multiply by the derivative of that thing, which is 3x squared plus 5. And if this thing also had another derivative inside it, I would keep going as far as I needed to go until I got to the middle. And just one more example with an ln in it. Something like that. If it had just been an x, it would have been 1 over x. But it's not an x, it's a 7x squared plus 1, so I have to times by the derivative of that, which is 14x. And that's how the chain rule works. And you can, it's called the chain rule because you can chain them all together in several layers as far as you need to go. So I find it most useful to think of it as I cover that up, pretend it's an x, do that, and then put it back, and then multiply by the derivative of that. Yeah. So when we were doing this thing, that's what happened here. ln of this, I covered that up and we did 1 over that, and then I multiplied by the derivative of that thing with respect to x2, which is x3. And so just for my completeness' sake, so f2 comes out to minus x1, x3 cubed on x2 squared, plus that x3 on the top will cancel with that x3 on the bottom, and I'll just get 1 over x2. Which is horrible. I am not a fan of this. But I'm just going to write it like this for future reference. Because I know I'm about to differentiate it again. So that's going to be easier for later. And f3 should be df on dx2, 3. Now the x1 and the x2 both count as constants this time, and they're both multiplied or divided, so they'll both still be there. And the derivative of x3 cubed is 3x3 squared. And then my ln will become 1 over whatever's inside the ln, but this time I'm doing the derivative with respect to x3, and so the answer is x2. Like that. You okay? All right. I should write this one that way as well, just for x3 cubed x2 to the minus 1. So I don't want to do the entire of this problem because they've now got 6 other derivatives to do, but I can do, they're all the first derivatives. They're all done now. And the second derivatives, there will be 9 of them because each of these is the first derivatives, and then I have to differentiate each of those with respect to all 3 of the variables. So f1 was equal to this, x3 cubed x to the minus 1. So f11 is differentiate this with respect to x1. That's what that means. So just to say, we start with f and we do d on dx1, and then we do d on dx1. That's what that means. That's what we're imagining that means. So we've already done d on dx1 to get to this, and so we'll do it again. And the x, that doesn't have an x1 in it, and so the answer will be 0. And f12 means start with f and do d on dx1 and then do d on dx2. That's what that means. Because it's 1 and then 2. And so I already did the 1 to get to here, and so I'll do d on dx2. And so the x3 cubed is a constant multiplied on, it'll still be there, and I'll get that, which is minus, I'm just going to leave it with the power of minus 2, if I'm honest. It's just no point trying to make it look prettier. And f213 will be do d on dx1 and then d on dx3. We've already done the d on dx1 to get to here, and the d on dx3. The x2 to the minus 1 is a constant multiplied on, so it'll still be there, and I'll get the derivative of this is that. And so that's f11, and f12, and f13 are those three answers. But if I wanted to do f21, I would need to start with f2, which was minus x, damn it. Minus x1, x3 cubed, x2 to the minus 2 plus x to the minus 1. That's what f2 was. This is not going to come out the same. I'm not happy about this. And f21 would be differentiating this with respect to x1. And so the coefficient of x1 here is minus x3 cubed x2 to the minus 2, and that doesn't have an x1 in it. And this is the same answer we got back here. So f12 should be f21 unless you've made your function extremely strange. And so on. I can do them all that way. And f22 would be this with respect to x2, which would be complicated again, and you could keep going if you wanted. This is the coefficient of this that's multiplied on. I'll have to multiply by the minus 2 and put that down by 1, and this one will be, and f23 would be differentiating this with respect to x3, and so the minus x1, x2 to the minus 2 will still be there, and then I'll have a 3x3 squared. And that'll go away because it doesn't have an x3. And then f31 and f32 and f33 will all exist as well. And so this question was actually asking you to do all 9 of them. Well, technically you don't have to do the 1, 1 and the 2, 2 and the 3, 3, but to do all 9 of them and show that the 2, 1 is the same as the 1, 2, and the 2, 3 is the same as the 3, 2, and the 2, 3 is the same as the 3, 2, yeah. 1, 3 is the same as 3, 1. Yeah. Okay. How are you feeling?
I get it. It's just a lot.
They wouldn't get you. He wouldn't get you to do this in an exam. He'd just get you to do one of them or something. I mean, he seems like a nice person. I wouldn't expect him to do anything like that. But this is the really important thing to keep track of, the chain rule. It takes some getting used to because the way that you do it on paper, like this, is not usually similar to the way that it's described in a book. Yeah. Okay. Doing well. I have that back. So the other thing that you were particularly worried about was the optimization stuff. I'm just going to have a quick peruse. Just checking that the recording was still on. And then there's the whole Lagrange multiplier stuff. And your worry about that was actually coming to solve the equations that appeared as you went. Cool, all right. And that is the hard bit, but I can't make it happen until we get to that bit. So I'm just going to do this. So there's two kinds of optimization in this course. There is unconstrained and constrained. So in unconstrained optimization, you have some function, it's often a u, which is something involving both x and y, or possibly a z as well, some sort of formula there, and you want to find the maximum or the minimum of u. And what you do is that the place where the maximums and minimums will happen is when all of the partial derivatives will be zero at the same time. So you need du on dx to be zero and du on dy to be zero at the same time. And the bit that you've described as the hard bit is once you've got these two equations involving x and or y, how do you put them together to figure out what the actual options are for x and y? Yeah. Just so we can compare the two of them, I'm going to write the other one down. Constrained optimization. It's the same, except there's a little bit of extra. So you've got some function involving x and or y, or some possibly more than one, and you still want to find the maximum and minimum of u, but subject to some constraints. You're saying, oh, we only want that, but only if we're spending all of our budget, or that's usually the constraint. I'm just going to see if I can find the way that your lecturer described it. Yeah, whatever. Oh, they do it that way, do they? Okay. Subject to some formula equals a constant number m. And so they call this phi. Oh, no, they don't. They call it curly phi. Of course they do. They call that. And this is a specific number. At the moment, it looks like it's an unknown, but it will usually be a specific number. And so what you're going to do is you're going to create a new function, which your lecturer has called g, which is your original function plus lambda times m minus this thing. So what you do have to do is you have to make this equal to 0 and then sub that thing in here next to the lambdas. And then what you're going to do is you need dg on dx to be 0 and dg on dy to be 0 and dg on d lambda to be 0. And it is technically possible to do this with two constraints simultaneously, and you can add a lambda and a mu if you want, and it'll all work out fine. Then you'll just have to make that happen. And dg on d lambda will come out to be this thing, and when that's equal, it'll be the constraint. So overall, they're not that different, other than before we do the derivative part in this one, we have to create this function. And this lambda here is called a Lagrange multiplier. Lagrange. I suspect he was French by the way you pronounce his name. And it's the Greek letter lambda makes an L sound, and so it's L for Lagrange. L for Lagrange. So in some other courses, they call this function curly L. Just in case, if you look it up online, you Google Lagrange multipliers. They'll call this curly L and they might call this something else, and all the letters will be different, but it'll be the same idea. So when they do it in, they don't do this until second year in the maths degree. And so when they do this, they call the function L. No, H. So anyway, gets me every time. Every different course calls it by different letters. That's my job as the Maths Learning Centre. I have to keep track of all those things. And so there is an example in here which says find the optimal value of x squared minus 3xy plus 12x subject to 2x plus 3y equals 6. So this is our classic optimization problem. This is the u that I was referring to. You could call it f, and this is the phi they were referring to. And so I would have to create a new function which they call g, which is the original function I was interested in, plus lambda times 6 minus 2x minus 3y. So your lecturer prefers it to be the plain number minus this stuff, but it shouldn't make any difference to the final answer. I would prefer it as 2x plus 3y minus 6 because there's fewer minuses, but there we go. And so we have to find what all of these things are, dg on dx. So this x, that'll become a 2x. The minus 3 and the y will still be there, and the derivative of x is 1, and this will be a 12. And then that lambda is a constant multiplied on, so it will still be multiplied on. And then the derivative of x here, derivative with respect to x of that inside is minus 2. So I just have to keep that mantra I have is this is a constant that's multiplied on, it will still be there afterwards, is really helpful for me with Lagrange multipliers. And so then dg on dy is, well, the x squared doesn't have a y in it, and we'd be just left with a minus 3x. And then there's a lambda multiplied on it still there, and we get a minus 3 from the y there. And this has to be 0, and this has to be 0. And then dg on d lambda, nothing else has a lambda except here, and the coefficient of lambda is 6 minus 2x minus 3y, which also has to be 0. And that's 3 equations in 3 unknowns. We don't actually care what the lambda is. We just want to use it to figure out what the x and the y are. That's we created the lambda ourselves in order to help solve the problem. So your lecturer does what I do, which is to label our equations. And somehow I have to figure out what to do with these equations. Cool. So there are choices for how you can do it, but ultimately what you want to do is make one equation that doesn't have a lambda in it. So from the ones that have lambda, you want to create an equation that doesn't have a lambda. Simultaneous equations, except, yep, it's going to be, I don't like it. So I'm just going to sort of make this look a little cleaner. So I've got from 1, I've got 2x minus 3y plus 12 minus 2 lambda is 0. And maybe I'll make that equal to 2 lambda. That seems like a good idea to me. Like that. I've moved the minus 2 lambda over that side. Minus 3x is equal to 3 lambda. So that's where I am now. I get to choose how I do this. What your lecturer did is they divided everything by 3, and you get that lambda is the same as minus x, and they subbed it in. That is my favorite plan. And so I'm going to go number 1 times 3. And so that's 6x minus 9y plus 36 is 6 lambda. And number 2 by 2, that's minus 6x is equal to 6 lambda. And now, if I subtract this one minus this one, so I shall call this number 4 and number 5. 4 minus 5, 6x minus 6x is 12x, minus 9y is still there, the 36 is still there, and I get a 0. And that is a perfectly good linear equation in x and y. And oh look, there's another one from equation number 3. So 12x minus 9y equals minus 36. And then equation number 3, it gives me 2x plus 3y is equal to 6. And now that's 2 equations and 2 unknowns, which I can solve by whatever methods you like. But the first step is to create an equation that doesn't have a lambda in it. And then you combine that with the other equation you've got from the constraint, and that should be enough to get what you need. And so then I guess we could times the second one by 3, and that would make the y's cancel out, and we could figure out what x is and then figure out what y is. I'm not a big fan of this minus 36 here, but that's okay. They didn't tell us what x and y were, so I presume they're allowed to be negative today. But in most economics applications, the x's and the y's are amounts of stuff, and so they can't be negative. But today they can, I think, for this problem. Oh, they get an x equals 1. I may have done something wrong in my working here. Well, I will see how it turns out, hey? I guess we have to times by 3. Have I done something wrong? Did I read the original question wrong? That's always a thing that happens. Anyway, we can continue from this point, because in this one, I don't think I've done anything wrong. 2x minus 3y, 12. Put the 2 lambda over there, and put the 3 lambda over there. And then we multiplied this one by 3. By 2. Okay, sure. How are you going to go about solving these two? Oh, by 6 to make this, to make the x's match? Is that what you're going to do? Yeah, okay. The other option is to multiply it by 3 to make the y's match. That would work too. So you multiplied it by 6, and so that gives you 12x plus 18y equals 36. And then you subtract the 2 of them, so you would go this minus this, or even better, this minus this. That would probably be better, wouldn't it? 7 minus 6. This minus this, that'd be go away. 18 plus 9 is 27, and 36 plus 36 is 72, and y would be whatever 72 on 27 is, well, the other way around. And they're both multiples of 9, interestingly, so that should be 3/8, which, if we're very lucky, is the answer. I've got 4/3. Oh crap, it's 72 on 27. Lecturer's got 8/3, and we've got lecturer's got 4/3, we've got 8/3. It doesn't really matter. We know how the process works now. Just really interested to see where our differences are. Oh, they did different things to us because they did subbing it in instead of multiplying by things. (4x) 6x. Oh, look. 6x plus 6 equals 0. When you move that 6 to the other side, it will become a -6. Yeah. Oh, well, it could be. You could be copying it down from... But that's what happened. I was expecting the x's to be negative from what we had. And then once you know what y is, you can sub it back into any of the equations you've got so far, and you can figure out what the x is. Yeah, I have to do it. Sub into number 3. And so we've got that 2x plus 3 times 8/3 is 6. So 2x plus 8 is 6. 2x is minus 2x is minus 1. And so whatever the optimal value is, whether it's a maximum or a minimum, and I do not actually know, occurs when x is minus 1 and y is 8/3. I have no idea if it's a maximum or a minimum. I can tell by going just a little bit further away from this and seeing if it's lower, but I have to move along that line, unfortunately. So that just makes it a bit trickier. Yeah, but that's okay. The question didn't ask us to make a decision about whether it was a maximum or a minimum, so we will. Or I could just figure out any one other point on that line and sub it into the value thing and see if it's higher or lower than this one. So just going to check something. The actual value is x squared minus 3xy plus 12x, which is minus 1 squared minus 3 times minus 1 times 8/3 plus 12 times minus 1. That's what the answer is going to be at that point. And so that's 1 minus minus, that'll be a plus 8 minus 12, which is negative 3. Doesn't feel like a maximum. Probably a minimum. But if I could find any one other point on this same line and sub it in, if it was higher, then I would know this was the minimum. Yeah. So I guess 3, 2 is on this line. 3 for x, no. 3 for x and 0 for y would work. 3 for x and 0 for y. Yep, 3 for x is a positive number, and so this is a minimum actually. But I don't know if they have to do that sort of thing. Okay, cool. So it is possible to not actually find any points at all, and there is no maximum or minimum. Yeah, okay. Well, that was all right. So that was good. So there is another problem in here that I was really interested in looking at actually, and it was the next one in this notes, and it was this one here. A monopolistic producer of two goods, G1 and G2, has a total cost function of this, where Q1 and Q2 denote the quantities of good 1 and good 2 respectively. If P1 and P2 denote the corresponding prices, then the demand equations are that find the maximum profit if the firm is contracted to produce a total of 15 goods of either type. Okay, that's an interesting question. The total cost is 10 times Q1 plus Q1 times Q2 minus 10 times Q2. Of course, no, plus 10 times Q2. That's cool. And price 1 is 50 minus Q1 plus Q2. And price 2 is 30 plus 2Q1 minus Q2. And we want maximum profit if Q1, the total of Q1 and Q2 has to be 15. Okay. So we haven't been given a function yet. We're going to have to make it ourselves. And so the revenue will be quantity 1 times price 1 plus quantity 2 times price 2, which will be quantity 1 times 50 minus Q1 plus Q2 plus quantity 2 times 30 plus 2Q1 minus Q2. Oh wow, sure, and why not? 50 Q1 minus Q1 squared plus Q1 Q2 plus 30 Q2 plus 2 Q1 Q2 minus Q2 squared. 50 Q1 minus Q1 squared. And now we've got 3 Q1 Q2s plus 30 Q2s minus Q2 squared. That didn't simplify very much. Oh well. And profit is revenue minus cost, yeah? So that'll be 50 Q1 minus Q1 squared plus 3 Q1 Q2 plus 30 Q2 minus... Wow, I really don't want to do this. Yeah. That's okay. Q2 squared minus the total cost. So we're going to go minus 10 Q1 plus Q1 Q2 and 10 Q2. Okay, so 50 Q1 minus 10 Q1 is 40 Q1s. The minus Q1 squared still there. The 3 Q1 Q2 minus 1 Q1 Q2 is now 2 Q1 Q2s. The 30 Q2 minus 10 Q2 is 20 Q2. And there's still at the end a minus Q2 squared, which I couldn't quite fit on the same line. Damn it. And that is what we have to maximize, subject to Q1 plus Q2 is 15. So we're going to create my function g, which is all of that. Plus lambda times the 15 minus Q1 minus Q2. All right. dg on dq1. So we'll have a 40 minus a 2q1 plus a 2q2. And these don't have q1s in them, so they're gone. And then the lambda is still there, and there'll be a minus 1 to go with that q1. And dg on dq2 is, that doesn't have any q2s. We'll have 2q1, so that's a 2q1, and then a 20, and then a minus 2q2, and then it'll be plus lambda and also minus 1, and that's supposed to be equal to 0. And then officially, dg on d lambda is the 15 minus q1 minus q2. It always works out that way. And that's supposed to be 0 as well. And somehow I have to get the ones that involve the lambdas to match up. And this one's actually going to be quite nice because the lambdas already match quite nicely. So if I did number 1 minus number 2, that might do the trick. So the 40 minus the 20 gives me 20, and the minus 2q1 minus another 2q1 is a minus 4 lots of q1, and a 2q minus minus 2q is a plus 4q2, and this minus this comes out to 0, and so I get this. So I just straight up subtracted them because the lambda times minus 1's already matched. That is very pleasant, actually. I can divide everything by 4. That's even better. So minus q1 plus q2 is minus 5. Awesome. So if I combine this with, from number 3, I've got q1 plus q2 is 15. So now if I add those two together, I'll get 2 lots of q2 is 10. So that plus that is 0, that plus that is 2 lots of q2, that plus that is 10, and so the q2 is actually 5. Look at that. And so since q2 plus q1 is supposed to be 15, therefore the q1 has to be 10. So I can sub it into any one of the equations I want, and the one that I like the best is the q1 plus q2 is 15. Therefore, q1 plus 5 is 15, and q1 equals 10. So that's really cool because that was much shorter than it looked like it was going to be. In fact, much shorter than the working that you've got. I just happened to notice that the lambda bit's already matched.
Yeah, this one is a lot easier.
Yeah. Now, it did actually say what is the maximum profit. We've just figured out the quantities that produce the maximum profit. And so the maximum profit is therefore this formula here with Q1 being 10 and Q2 being 5. So the maximum profit will be 40 times Q1, which is 10, minus Q1 squared, plus 2 times 10 times 5, plus 20 times Q2, which was 5, minus Q2 squared, which is 5 squared, which will be whatever the answer is. 400 minus 100 is now 300, plus another 100 is 400, plus another 100 is 500, minus 25 would be 475. I think if I'm extremely lucky, that's what calculators are for. So
simplifying really long.
Yeah. And that is the goal. Make all the lambdas go away as early as you can because you don't need them. They're just there to help you solve the problem. Yeah. Officially, there is a meaning for what the lambdas mean. The lambda does mean something, but I can never remember what it is. It's something I can't remember. It's something to do with how much the budget makes a difference to the results. Because that's what it does. This is the budget. In our case, it's not the budget, it's the total number of goods, but yeah. So there you go, that's what our final profit is. If we were absolutely, we really don't know if that's a maximum or a minimum. And so you could pick a different value of Q1 and Q2 that adds up to 15 to see what that works out to be. Because if it's lower, then that would make this definitely a maximum. So just to check, if Q1 is 0 and Q2 is 15, the profit comes out to 40 times 0 minus 0 squared plus 2 times 0 times 15 plus 20 times 15 minus 15 squared. And all of these are 0, which is convenient. 20 lots of 15 would be 300. which is less than 475 because it's less than 300. All right, so it really is a maximum, so that's good. Because at some other place it's slower, and so it has to be the highest one. All right, because that's the worry, right? This doesn't actually tell you whether it's a maximum or a minimum, and what we could have found was the minimum profit, in which case the maximum profit would have to happen at one of the other ends. So if this was the minimum profit, then you would go, well, the maximum profit would have to happen at either one end of the line or the other end of the line, which would be when Q1 is 0 or when Q2 is 0. But I'm pretty sure the lecturer wouldn't go do that sort of sneaky trick in the exam. Yeah. Cool. I might leave it at that, if that's okay.
Yeah, that's fine. I think that's all the problems that I had.
There you go. You're welcome. I'll stop the recording.